Alright people, welcome back. So in today's episode we're dealing with min cost climbing stairs. So I didn't read this problem before starting the recording, so let's look at it together. You are given an integer array cost, where cost I is the cost of the ith step on a staircase. Once you pay the cost, you can either climb 1 or 2 steps. You can either start from the step with index 0 or the step with index 1. Return the minimum cost to reach the top of the floor. Oh wow, this seems really nice. Okay, so it's a cost optimization problem. We have exactly, like for example, the cost is not increasing. The cost can be very different from step to step. So for example here, I think we should start with 1, then we skip to 1, then we can skip to 1 here. But then of course we want to skip, and then like climbing of 2 steps is not efficient. We climb on just 1 step and then we go to the end and reach the top, so that we don't pay those 100 costs that we can see in the array. Okay, but with that we need intelligence. We need intelligence. We don't need just to climb more than two steps each time. We need also to be intelligent and to see what's going to happen in 3 steps, for example, then decide, for example, to climb only 1 step this time. Okay, again, we can think about this problem with a dynamic programming approach. So let's directly start from the end. Suppose now we can arrive at the last step. We can reach the top with the step n minus 1 and the step n minus 2, right? Yes. But now the question is, which is the less expensive? So I need to compute the less expensive path that brings me to 100 and the less expensive path that brings me to 1. And then summing the costs for climbing these 2 steps, I'll get to the less expensive. How do I get to the less expensive that brings me here? I just compute all the possible paths that bring me to 1, which are the less expensive one that brings you to 100, plus the less expensive one that brings you to 1, and so on and so forth. Okay, until I get to 100, for example. The less expensive path that brings you to 100 is just 1, and the less expensive path that brings you to 1, for example, is nothing, is 0. Okay, so I think we can approach this. So let's call it dp. dp is a list, which is the input. Cost is, we have a list costs, and we can compute n as the length of cost. Okay, and then we can define a dp, which is just equal to this times n, actually n plus 1, because this is the last step before reaching the top. So what we're interested in is dpn. This is our value that we want to calculate, so the minimum cost to reach the top. Okay, now we can define for sure dp0. dp0 is equal to 0, and dp1 is equal to I think it's cost 0. Oh, actually I can start at 0, at 1, or at the index 0 or at index 1. So I think dp0 and dp1 are this. Let me think. Okay, so no, I think this is correct. So we don't need to initialize dp0 and dp1 at this point, because of course they're already initialized here. And then what we can do is to simply say for I in range 2 n plus 1, what we do is simple. We store dpi as dpi as the minimum between dpi minus 1 plus cost I minus 1 and dp I minus 2 plus cost I minus 2. What do you think of this? So we're actually computing the path with lowest cost until I. And that's it. And then we return dpn. I don't know if this is going to work. I don't expect this to work. Yeah, here of course we need to add parentheses. Wow, guys, it worked. That is crazy, really. That is crazy that it worked. I didn't really understand why it's working. Wow, okay. So I don't know if this is the most efficient solution, but actually, memory-wise, it's on again. Complexity, like in terms of time complexity, it's on too. I think we can avoid using, looking back at the problems we solved in the previous episodes, I noticed that maybe we can avoid defining a list and we can just store the last 3 values, which we can try to do now actually. But in general, the idea is that we have this range and then we initialize the minimum cost at level I as the minimum between the cost of level of doing length 1 step at level I minus 1 plus the cost of all the minimum path of the minimum cost that brought me to step I minus 1. And the cost of going from level I minus 2 to level I plus the minimum cost of getting to level I minus 2. And if you do this on and on until you reach index n, which is going to be element n plus 1, you get to the solution, which makes sense, absolutely, but I was surprised that it actually worked. So yeah, guys. It feels like we solved the problem. Now I think this can be optimized memory-wise. Yeah, so I had this idea while looking at the previous problems that we solved. I think what I'm going to do now is very similar to what we could have done with the previous problems, which is here we are storing an entire list, and this requires on memory complexity. This is not necessary, because what we can do is instead of calling this DPI, we can call it current. We just need, each time we need to store 3 values, which are the current values, the previous, let's call it the previous value 1 step from current, and then the previous value 2 steps from current. And then each time we just have to update, once we updated current, then how can we yeah, of course, previous 1 is going to be current and previous 2 is going to be previous 1. Actually, maybe it's better to write it down this way. So we initialize previous 2 as previous 1, and then we initialize previous 1 as current, and then we go on and on. Then of course we need to initialize somewhere previous 2 and previous 1, and the cost, this is the cost of getting to the first level and the 0 level, the first and the second level, which is 0, the minimum cost. Yes, so this is going to be 0 and 0, and we return current, of course, and this should work. Yes, it does. Yes, it does. Okay, you see what we changed here? We just avoided creating a list. We are just iterating the storage of 3 different values, and this is enough. So this is time complexity on and memory complexity O1. Great. Okay, guys, thank you very much for watching this video, and see you in the next episode.